TON 618 is the most colossal quasar ever observed. How can a single object shine with the intensity of billions of suns, while also harboring one of the greatest mysteries of modern cosmology? At the center of this cosmic titan lies a supermassive black hole whose size and power exceed imagination. But what does it really mean for something to be so massive and so distant that its light has traveled billions of years before reaching us? Quasars are much more than simple points of light in the sky. They are beacons of the primitive universe, windows into a time when galaxies were in full formation and the cosmos was a violent and chaotic place. TON 618 stands out among them, not only for its astonishing brightness, but because it allows us to explore fundamental questions. How do black holes grow to such monstrous masses? What role do they play in the evolution of galaxies and the universe itself? Imagining the scale of TON 618 is a fascinating exercise. If the entire solar system could be placed next to this monster, it would be dwarfed to the point of insignificance. Its light, emitted when the universe was just a fraction of its current age, reaches us as an echo of a distant past, laden with information about the early chapters of cosmic history. Every photon we detect whispers secrets about extreme physics, about matter and energy in conditions we will never be able to recreate on Earth. Why does studying TON 618 matter so much? Because its existence condenses the great enigmas of astronomy, the origin of cosmic structures, the nature of gravity beyond known limits, and the ultimate fate of the most extreme objects. Deciphering its secrets is peering, even if briefly, into the deep mechanics of the universe, and better understanding our own place in the vastness of the cosmos. What makes a quasar so special in the universe? The answer begins in the farthest and oldest corners of the cosmos, where these extraordinarily bright objects reside. A quasar, whose name comes from quasi-stellar radio source, is the hyperluminous core of a distant galaxy, powered by the energy released when matter falls into a supermassive black hole. But how can something so small, compared to an entire galaxy, emit more light than the hundreds of billions of stars that inhabit it? The key lies in the extreme violence of its environment. Quasars are, in essence, cosmic beacons visible at unimaginable distances. They are not stars, although for a long time they were thought to be due to their point-like and bright appearance. In fact, their light has traveled for billions of years before reaching us, allowing us to observe what the universe looked like when it was just beginning to form. The source of their extraordinary brightness is the accretion process. The gas and dust spiraling into the supermassive black hole are heated to tremendous temperatures, emitting energy across the electromagnetic spectrum, from radio waves to X-rays. But why are quasars so energetic? If we could compress the energy that the sun emits over its entire life into just a few seconds, we would be approaching the power of a quasar. In their cores, the material trapped by the black hole's gravity spins at speeds close to the speed of light, generating extreme friction and heat. This energy is released in the form of radiation, which can exceed the luminosity of entire galaxies. In other words, the quasar is the result of one of the most efficient mass-to-energy conversion processes in the known universe. Moreover, not all quasars are the same. Some show spectra dominated by radio emissions, while others are more active in the ultraviolet or X-rays. What they all have in common is that they are indicators of supermassive black holes that are rapidly growing, devouring matter at astonishing rates. Quasars are not only natural laboratories for studying extreme physics, but they also provide us with crucial clues about the early evolution of galaxies and the black holes themselves. Thus, each quasar is a window into the distant past of the universe and a reminder of the most powerful mechanisms shaping the cosmos. How is it possible that one of the most colossal objects in the universe went unnoticed for so long? The story of the discovery of TON 618 is a fascinating example of how curiosity and technology go hand in hand to reveal the secrets of the cosmos. It all began in the 1950s, a time when radio astronomy was just taking its first steps and the catalogue of celestial objects was much smaller than it is today. During those years, astronomers were systematically recording the sky, searching for stars and galaxies with unusual characteristics. However, no one imagined that among the seemingly insignificant points, one of the most impressive entities ever detected was hidden. Who was the first to notice something strange? In 1957, a group of Italian astronomers, led by the Turin Observatory, embarked on an exhaustive exploration of the sky using photographic plates sensitive to ultraviolet light. Their goal was to identify hot blue stars, but in the process, they stumbled upon an object that did not fit any known category: TON 618. The name comes precisely from this search: Turin Observatory number, followed by the assigned number in the catalogue. Why did this object catch their attention? Because unlike common stars, its spectrum showed atypical emission lines and a surprisingly high luminosity for its apparent distance. At first, no one suspected it was a quasar. At that time, the concept of a quasar did not yet exist. In fact, the very word quasar would not be coined until the 1960s. TON 618 was simply catalogued as a peculiar blue star, with no clear explanation of its nature. It was not until years later, when advances in spectroscopy allowed for a more precise analysis of the light it emitted, that astronomers noticed an unusually high redshift. What did this mean? That the object was much farther away than previously thought, and, therefore, had to be incredibly luminous to be visible from Earth. The true identity of TON 618 took time to come to light. A paradigm shift in astrophysics was necessary for scientists to understand that they were dealing with the active nucleus of a distant galaxy powered by a supermassive black hole. Thus, a simple blue dot on an old photographic plate transformed into one of the most astonishing enigmas of the observed universe. Who would have imagined that, in an apparently mundane corner of the sky, the most colossal quasar ever identified was hiding? The discovery of TON 618 not only expanded our knowledge of extreme objects in the cosmos, but also demonstrated that sometimes the greatest mysteries are right in front of us, waiting to be uncovered.
If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey.
TON 618 is undoubtedly an object that challenges our understanding of what can exist in the universe. But where exactly is this cosmic colossus located? TON 618 resides in a region of the sky that appears calm at first glance, in the constellation Canis Venatici. However, what makes it truly fascinating is not just its position, but the immense distance that separates it from our planet. It is estimated that its light has traveled over 10 billion years to reach us. This means that when we observe TON 618, we are actually seeing how the universe looked when it was just a fraction of its current age. Now, how bright is this quasar from our perspective on Earth? Its apparent magnitude is around 15, which means it is completely invisible to the naked eye and can only be detected with powerful telescopes. But this should not deceive us. Although its light may seem weak, TON 618 is actually one of the brightest sources in the entire cosmos. If we were to place it in the position of the Sun, its glow would be so overwhelming that it would completely eclipse all the stars in the night sky. Have you ever wondered how we manage to measure such colossal distances in the universe? For objects as distant as TON 618, astronomers use a tool called redshift. As the universe expands, the light from distant objects stretches and shifts toward the red end of the spectrum. By analyzing this phenomenon in the light coming from TON 618, scientists have been able to determine its astonishing distance and therefore its age. Finally, it is worth noting that TON 618, despite being so far away and so young in cosmic terms, continues to amaze us with the information it provides. It is a kind of time capsule, a window into an era when the first galaxies and supermassive black holes were in full bloom. Every piece of data we obtain about its location, distance, and brightness helps us reconstruct the history of the universe and understand how the most extreme structures emerged, challenging everything we thought was possible. Why is the light from TON 618 so fascinating to astronomers? The answer lies in the incredible amount of information it carries across unimaginable cosmic distances. TON 618 does not shine like an ordinary star. Rather, its light is the result of extreme processes at the heart of a distant galaxy. When scientists study this light, they are actually analyzing a message that traveled for billions of years, traversing the universe to reach us. Each captured photon is a time capsule, revealing what the cosmos was like when the light departed from this colossal quasar. But what makes the light from TON 618 different from that of other objects in the sky? Unlike sunlight, which comes from nuclear reactions, the luminosity of this quasar originates from the frantic dance of matter around its central black hole. As gas and dust fall at dizzying speeds into the gravitational abyss, they heat up to temperatures far exceeding those of any oven on Earth. This process releases energy in the form of radiation that spans almost the entire electromagnetic spectrum, from radio waves and microwaves, through visible and ultraviolet light, to powerful X-rays and gamma rays. Is it possible to see the light from TON 618 with the naked eye? The answer is no. Although it is one of the brightest known objects, its impressive distance makes it an extremely faint point from our planet. However, when telescopes capture its light, the resulting spectra show very particular emission lines. These lines act like fingerprints, allowing scientists to identify the elements present near the black hole and estimate the speed at which it is receding, due to the expansion of the universe. The light from TON 618 not only reveals its power, but also the secrets of the environment where it is born. For example, by analyzing the spectrum, astronomers can deduce the amount of matter in the accretion disk, the presence of galactic winds, and even the intensity of magnetic fields. Thus, every beam of light that reaches us is much more than a simple flash. It is a direct window into one of the most extreme and energetic phenomena in the universe, challenging our understanding of how matter and energy interact at the limits of known physics. What lies at the heart of TON 618? At the center of this colossal quasar is one of the most massive black holes ever detected by humanity. But what does it really mean for it to be a supermassive black hole? A black hole of this kind is not simply a region where gravity is so intense that nothing can escape, not even light. It is, moreover, a cosmic monster whose mass defies everything we could imagine in the known universe. To get an idea, the mass of the black hole at the core of TON 618 is so overwhelming that it exceeds billions of times the mass of the Sun. If we were to compare, it would be like gathering millions of small galaxies and concentrating them into a single invisible point. This black hole is so immense that if we replace the Sun with it at the center of our solar system, its event horizon would extend far beyond the orbit of Neptune. Can you imagine it? What is for us the vastness of the solar system would be barely the edge of its gravitational shadow for TON 618. Why can such a colossal black hole form? The answer lies in the extreme processes that occurred in the early times of the universe, when galaxies were young and chaotic. During those periods, enormous amounts of gas and dust fell toward the centers of proto-galaxies, feeding active nuclei and allowing these black holes to grow at dizzying speeds. In the case of TON 618, this process was so efficient that it reached a record size in a surprisingly short time, challenging many of the current theories about the growth of these cosmic giants. But how does a black hole of such magnitude affect its surroundings? Contrary to popular belief, the black hole is not simply a silent devourer. Its presence generates gravitational forces so intense that they shape the structure of the entire host galaxy. Moreover, by attracting and consuming matter, it releases colossal amounts of energy in the form of radiation, causing the quasar to shine with an intensity that surpasses trillions of stars combined. Thus, TON 618 not only hides an unfathomable abyss in its core, but also dominates and transforms the cosmos around it. leaving an indelible mark on the history of the universe. What is the true magnitude of the monster that resides in the heart of TON 618? To answer this question, it is first necessary to understand how astronomers can estimate the mass of a black hole that is billions of light years away. They use various techniques, such as analyzing the movement of material orbiting the black hole, or measuring the brightness of the quasar and its spectrum. In the case of TON 618, studies have revealed that its supermassive black hole challenges our conceptions of what is possible in the universe. Current estimates place the mass of this black hole at around 40 billion times the mass of the Sun. To put this figure into perspective, if the Sun were the size of a marble, the black hole of TON 618 would be like a gigantic, crushing, and immeasurable mountain. It is so colossal that it surpasses most known supermassive black holes, even those residing in the centers of enormous galaxies like the Milky Way or the Andromeda Galaxy. While our central black hole has a mass of about 4 million solar masses, TON 618 raises the stakes to nearly unimaginable levels. But how can something so massive exist? The explanation lies in the processes of accretion and galaxy mergers over billions of years. The central black hole of TON 618 has devoured enormous amounts of matter, engulfing gas, dust, and possibly even other black holes. Each time an object falls into it, the mass of the black hole grows, and in turn, its gravitational influence becomes even more powerful. The result is a cosmic titan whose mass challenges current theoretical limits on the growth of these objects. The mere existence of such a massive black hole raises profound questions about the evolution of the early universe. How long did it take to reach such a size? Were there special conditions at that time that favored the rapid growth of these giants? TON 618 is undoubtedly one of the best examples of the cosmos's ability to create structures that defy our imagination and test the most advanced models of astrophysics. When we talk about supermassive black holes, it's inevitable to wonder, how exceptional is the one that resides at the heart of TON 618? To put it into perspective, let's think about some of the most famous black holes in the known universe. For example, Sagittarius A, the central black hole of our own galaxy, the Milky Way, has a mass of approximately 4 million times that of the Sun. The black hole in Messier 87, in the nearby elliptical galaxy, was the first to be photographed and boasts a mass of about 6.5 billion suns. But how does TON 618 compare to these cosmic titans? The answer is astonishing. The black hole of TON 618 has an estimated mass of over 66 billion times that of the Sun. This places it in a completely different league, far surpassing even the most studied and nearby supermassive black holes. If Sagittarius A's were a coin, the black hole of TON 618 would be a mountain. Its size challenges the imagination and raises profound questions about the limits of growth for these extreme objects. Are there other black holes that come even close? There are some notable candidates, such as the black hole in the galaxy Holmberg 15A, estimated to be around 40 billion solar masses, or IC 1101, which could reach 40 billion solar masses. However, none have been confirmed with such certainty or show luminosity as extreme as that of TON 618. Thus, while other supermassive black holes are impressive, TON 618 continues to reign as the undisputed colossus. This comparison leads us to a fascinating question. How is it possible for a black hole to reach such size in such a short time, considering the age of the universe? The existence of TON 618 challenges current theories about the formation and growth of black holes. Some models suggest successive mergers of smaller black holes, while others propose extremely high accretion rates in the early universe. In any case, TON 618 stands out not only for its numbers, but also for the mystery it represents in cosmic evolution. What does it really mean for something to be bright in the universe? When we think of luminous objects, we often imagine stars like the Sun, or perhaps a supernova exploding in the depths of the cosmos. But what if I told you that there are objects that surpass all the stars of a galaxy combined? TON 618 is one of them. Its brightness is not only enormous, it is so colossal that it defies any comparison with everyday light sources, or even the most extraordinary ones we know. Quasars, and especially TON 618, can emit more light than trillions of suns combined. But how is such luminosity measured? Astronomers use a scale called bolometric luminosity, which includes all the energy that an object emits across all wavelengths, from X-rays to radio waves. In the case of TON 618, its estimated luminosity is over 100 trillion times that of the Sun. To put this into perspective, if the Sun were a simple household bulb, TON 618 would be like a gigantic lighthouse illuminating an entire continent. Its brightness is so intense that, despite being billions of light years away, we can still clearly detect it from Earth. Where does this colossal energy come from? The key lies in the process of accreting matter by the supermassive black hole at its core. As gas and dust fall toward the black hole, they heat up to extreme temperatures and release enormous amounts of energy in the form of light. It is such an efficient process that it converts a significant fraction of the mass into energy, much more than the nuclear reactions that power stars. That's why, during its peak activity, a quasar like TON 618 can outshine the combined brightness of all the stars in its host galaxy. Can anything compete with the brightness of a quasar like this? Even the largest and brightest galaxies pale in comparison to the intensity of TON 618. If it were much closer to us, its glow would be such that it could rival that of a full moon in the night sky, despite being a distant and tiny source in comparison. Its luminosity makes it a cosmic beacon, visible through the vastness of the universe, and essential for understanding the most extreme and energetic objects that exist. In short, TON 618 is not just bright, it is one of the most powerful torches that has ever lit up the cosmos. What happens when an unimaginable amount of gas and dust falls into a colossal black hole like TON 618? The answer lies in the fascinating phenomenon of the accretion disk. This disk is a gigantic whirlpool of matter spinning at breakneck speeds, as if the black hole's gravity were mixing the ingredients of a cosmic recipe. But why is this disk so crucial in the case of quasars? The reason is that before being devoured, the matter in the disk heats up to extreme temperatures, emitting enormous amounts of energy in the form of light and radiation. It is precisely this that makes quasars so bright and detectable, even at unimaginable distances. In the case of TON 618, the accretion disk is so massive and active that it outshines entire galaxies. Imagine a structure larger than our solar system, spinning at a speed such that the friction between particles causes them to shine brighter than 1,000 trillion suns combined. The gas and dust spiral inwards, compressed by colossal gravitational forces, until they reach regions where the temperature can exceed millions of degrees. This extreme heat causes the emission of radiation at different wavelengths, from X-rays to visible light, turning the accretion disk into a true cosmic power plant. Are you wondering what happens to the matter that fails to escape the disk? As the material approaches the center, some of it is ejected into space in the form of powerful jets, but most ends up crossing the so-called event horizon, the point of no return of the black hole. Before that final fate, the gas and dust undergo a radical transformation. Friction and gravitational forces generate intense magnetic fields and accelerate particles to speeds close to the speed of light. This process is so violent that it can influence the galactic environment millions of light years away. But the accretion disk of TON 618 is not only fascinating for its size and energy, but also for the mysteries it holds. How can such a gigantic structure remain stable? Astronomers are still investigating how the accretion rate is regulated, that is, the amount of matter falling every second, and how this balance affects the growth of the black hole. What is clear is that without the accretion disk, TON 618 would be invisible to us. It is this ring of cosmic fire that makes the difference between a black hole hidden in darkness and the most colossal quasar ever observed. What happens when matter gets dangerously close to a supermassive black hole like TON 618? As gas and dust fall toward its center, not all of this matter disappears into the abyss. A fraction is redirected and expelled in the form of relativistic jets, streams of particles that emerge from the poles of the black hole at speeds close to the speed of light. This phenomenon is one of the most energetic and extreme spectacles in the known universe. But how is it possible for the core of a galaxy to launch material so far and so fast, defying the gravitational force that should keep it trapped? The key lies in the magnetic fields generated near the black hole. Imagine a cosmic dynamo. The accretion disk, spinning at dizzying speeds, twists and amplifies these magnetic fields until they become true energy cannons. These fields channel part of the accumulated matter and energy, launching them in the form of jets that can extend across millions of light years. It's as if an invisible tornado picked up the surrounding gas and shot it straight into deep space. These relativistic jets are not only impressive for their speed, but also for their impact on the environment. Can you imagine the effect of a particle hose launched at nearly the speed of light? Where these jets strike, they can heat and sweep away interstellar gas, regulating the birth of new stars in the host galaxy. The jets from TON 6M18 carry enough energy to sculpt the galactic medium on gigantic scales, leaving traces that astronomers can detect even at cosmological distances. Moreover, these jets are natural beacons that help us study the farthest reaches of the universe. The accelerated particles within the jets emit radiation across multiple wavelengths, from radio waves to X-rays and gamma rays. By analyzing this light, scientists can decipher the composition, speed, and direction of the jets. Thus, TON 6M18 is not only a cosmic monster that devours matter, but also a source of fundamental clues to understand the most extreme and mysterious processes occurring near supermassive black holes. What other secrets could these cannons of matter and energy be hiding? The study of relativistic jets continues to challenge the limits of our knowledge about the universe. How long has the light from TON 6M18 traveled to reach us? To answer this question, we first need to talk about redshift, one of the most fascinating concepts in modern astronomy. Redshift is a phenomenon that occurs when the light from a distant object is stretched to longer wavelengths due to the expansion of the universe. It's as if the universe were a balloon inflating, and as light travels, it has to cover more and more space, becoming redder in the process. Why is this important? Because the farther away an object is, the greater its redshift, and the older the signals we receive from it. TON 6M18 has a redshift of approximately 2.2. What does this mean in cosmic terms? It means that the light reaching us from this quasar left its source over 10 billion years ago, when the universe was just a fraction of its current age. In other words, looking at TON 6M18 is like seeing the deep past of the cosmos, observing a time when galaxies were just beginning to form and supermassive black holes like the one in this quasar were in the midst of their growth spurt. How far away is TON 6M18? The exact value depends on how the expansion of the universe is calculated, but current estimates place this quasar about 10 billion light-years from Earth. To put it in perspective, if the history of the universe were a single day, the light from TON 6M18 would have begun its journey when only the first few hours had passed. This incredible journey of light allows us to study not only the quasar itself, but also the conditions of the early universe. Redshift not only tells us how far away TON 6M18 is, but it also acts as a kind of cosmic time machine. Thanks to it, astronomers can reconstruct the history of the universe by measuring how quasars change over the ages. Is it possible that there are even more distant and ancient objects waiting to be discovered? Every time we observe a high redshift, we get a little closer to answering the big questions about the origin and evolution of the cosmos. Have you ever wondered how old the universe was when the light from TON 6M18 began its journey towards us? We're not talking about a recent past, nor even the time when dinosaurs walked the Earth. We're going back to a cosmic era so distant that it's almost unimaginable. When TON 6M18 shone with all its intensity, the universe was very young, barely a fraction of its current age. To put it in perspective, if the entire universe were a 100-year-old person, TON 6 and 18 would have existed when that person was only about 6 to 8 years old. In scientific terms, the light we see today from TON 618 was emitted when the universe was approximately 4 billion years old, much less than half its current age, which exceeds 13 billion. This means we are observing a sort of ancient photograph, captured at the moment when the first galaxies were forming and the universe was still in the process of maturation. Why is this so fascinating? Because it allows us to peek into a time when cosmic conditions were radically different from what we know today. Back then, the universe was a much more compact and hotter place. Galaxies were much closer to each other, and supermassive black holes, like the one residing at the heart of TON 618, were just beginning to reveal themselves as the titans we know today. It's astonishing to think that the light that now dazzles us traveled billions of light years, passing through clouds of gas, dust, and ever-changing cosmic structures, just to finally reach humanity's telescopes. This window into the past is not just a scientific curiosity, but a fundamental tool for understanding how the universe evolved. What does TON 618 tell us about cosmic infancy? That even in those early chapters of universal history, there were objects of colossal scale and power. The fact that we can observe it today is like finding a perfectly preserved fossil that reveals secrets about the formation of the first galaxies and the rapid emergence of gigantic black holes. Thus, TON 618 not only shines for its intensity, but also for the immense historical value of the light it sends us from a time when the universe was still a child. Observing a quasar located billions of light years away, like TON 618, is one of the greatest challenges in astronomy. How is it possible to capture signals from such a distant and ancient object? The key lies in the combination of advanced technological tools and scientific patience. Astronomers use large aperture optical telescopes, such as those installed at the Mauna Kea observatories in Hawaii or in the Atacama Desert in Chile. These instruments collect the faint light that has traveled for over 10 billion years, allowing for the analysis of both the intensity and composition of that radiation. However, the observation of a quasar does not end in the visible spectrum. Is visible light enough to understand TON 618? The answer is no. To unravel its secrets, astronomers turn to telescopes that capture radiation in other ranges of the electromagnetic spectrum, such as X-ray telescopes and radio telescopes. For example, the Hubble Space Telescope has allowed for the capture of details in ultraviolet light, while the Chandra Observatory focuses on the X-rays emitted by the quasar. Radio telescopes, like those that make up the Very Large Array Network, help detect the radio emissions produced by the relativistic jets. Why is it useful to observe in so many different wavelengths? Because each one reveals a different facet of the quasar, from the accretion disk to the particle jets and the interaction with the galactic environment. But how is TON 618 distinguished from other distant objects? This is where spectroscopic analysis comes into play. By breaking down the light from the quasar into a spectrum, scientists identify characteristic lines that act as a kind of fingerprint. These lines allow for the calculation of the redshift, which is the key to estimating the distance to TON 618. Additionally, the spectrum reveals details about the chemical composition of the material surrounding the black hole and offers clues about the extreme physical conditions that prevail in that region of the universe. The observation of TON 618 is, in fact, a collective and global effort. Data obtained from different observatories are combined and compared, allowing for a more complete picture of the quasar to be constructed. International campaigns are even conducted in which several telescopes observe the same object simultaneously, maximizing the amount of information collected. Thus, through collaboration and technology, humanity is able to peek into one of the most distant and mysterious corners of the cosmos, unraveling the secrets of a quasar that, despite the distance, continues to illuminate our understanding of the universe. What makes an object like TON 618 so relevant to cosmology? The answer goes far beyond its colossal size. This quasar is like a window into the distant past of the universe, allowing astronomers to observe what the early stages of galaxy and supermassive black hole formation were like. By analyzing the light that reaches us from such abyssal distances, scientists can reconstruct the history and evolution of matter in the cosmos. Why is this so important? Because understanding how gigantic structures like TON 618 formed helps decipher the mechanisms that shape the universe as we know it today. TON 618 also raises fundamental questions about the limits of cosmic growth. How could a black hole of such magnitude exist when the universe was still young? Traditional models of galactic evolution and black hole formation are challenged by the existence of such massive quasars in such early times. This forces scientists to reconsider and refine their theories, seeking alternative explanations for the accelerated growth of these cosmic monsters. Like a puzzle with no missing pieces, TON 618 invites us to seek answers where we previously didn't even know there were questions. Another reason why this quasar is crucial for cosmology is that it acts as a kind of beacon, illuminating the gas and matter that lie between it and Earth. By studying how its light is absorbed and modified by intergalactic material, astronomers can gain insights into the composition, distribution, and evolution of matter in the primitive universe. It's as if TON 618 were a flashlight that, although extremely distant, reveals invisible details of the vast space that separates us. Finally, the study of quasars like TON 618 allows us to test physical laws under extreme conditions, where gravity, energy, and matter interact in almost incomprehensible ways. How far can the forces of nature reach? Are there limits to the formation of supermassive black holes? Each observation and analysis of this quasar provides valuable data to refine theories about the evolution of the universe, the formation of galaxies, and the dynamics of the most extreme black holes known. Thus, TON 618 is not just an impressive object, but an essential key to unraveling the deepest mysteries of the cosmos. What role can a colossal quasar like TON 618 play in the formation and evolution of galaxies? This question has fascinated astronomers for decades because quasars are not mere spectators of the universe. They act as cosmic engines capable of completely transforming their surroundings. To understand this, it is essential to imagine a young and chaotic galaxy filled with gas, dust, and newly born stars, at the center of which a supermassive black hole, like that of TON 618, devours matter with insatiable voracity. In that process, it releases enormous amounts of energy that can influence everything around it. When a central black hole grows to these scales, the resulting quasar can emit radiation and winds so powerful that they act as a kind of galactic regulator. How does this happen? The energy released by the quasar can heat or even expel gas from the host galaxy, slowing down the formation of new stars. It's as if the galactic core ignited a giant fan that disperses the material needed for more stars to be born. In some cases, however, these winds can also compress gas clouds in certain regions, triggering bursts of star formation. Thus, quasars can both hinder and stimulate star creation, depending on local conditions. Can a quasar alter the fate of an entire galaxy? Evidence suggests that it can. Scientists have observed that galaxies with very active quasars tend to evolve differently than those where the central black hole is less energetic. This phenomenon, known as feedback, is key to explaining why there is such a close relationship between the mass of supermassive black holes and the mass of galactic bulges. In simple terms, the growth of the black hole and the development of the galaxy go hand in hand, as if it were a cosmic dance in which both influence each other. TON 618 represents one of the most extreme examples of this interaction. Its energy may have shaped the galaxy in which it resides, determining how many stars formed and how the galactic structure evolved over time. Analyzing such extreme cases helps us answer fundamental questions. Why do some galaxies stop forming stars so early? What mechanisms control the growth of the most massive galaxies? Thanks to the study of quasars like TON 6 and 18, astronomers are gradually unraveling the secrets of galactic evolution, discovering that, in the universe, the brightest protagonists can also be the most influential architects. What really surrounds a cosmic monster like TON 618? When we think of quasars, we often imagine just the bright core, but around this colossus extends a galactic environment as fascinating as it is mysterious. TON 618 is located in the heart of a distant galaxy, but what is that galaxy like and what happens in its surroundings? Astronomers have detected hints that its environment is composed of enormous amounts of ionized gas, interstellar dust, and likely other stars and planetary systems orbiting far beyond the direct threat of the central black hole. Have you ever wondered what happens to the material that fails to cross the event horizon? Part of that gas and dust forms dense clouds that spin chaotically, feeding the accretion disk and producing intense galactic winds. These winds, driven by the radiation from the quasar, can travel distances of hundreds of thousands of light years, carrying with them matter and energy. In a way, the environment of TON 618 is like a cosmic storm reshaping the entire host galaxy, affecting the formation of new stars and altering the fate of its galactic neighborhood. Despite its immense distance, scientists have managed to observe some traces of the interaction between the quasar and its environment. For example, the light from TON 618 reveals the presence of gas clouds that absorb and re-emit radiation at different wavelengths. This effect, known as absorption and emission lines, acts like a kind of cosmic fingerprint, allowing astronomers to decipher the composition and dynamics of the matter surrounding the quasar. What if I told you that the environment of TON 618 might contain regions where the matter is so energized that even the most resilient molecules cannot survive intact? But perhaps the most astonishing thing is that the environment of this quasar is not static. It is in constant transformation due to the brutal influence of the supermassive black hole. Relativistic jets and intense radiation can disperse the surrounding gas, inhibiting star formation in certain areas, while in other regions, they can compress the material and trigger the birth of new stars. Thus, TON 618 is not only a beacon in the early universe, but also a cosmic sculptor actively shaping its environment, leaving an indelible mark on the evolution of its galaxy. What other secrets could this extreme environment hold, still beyond the reach of our current telescopes? How is it possible for a black hole to become as enormously massive as TON 618? This is one of the big questions that intrigue astrophysicists around the world. Conventional theory tells us that black holes grow by feeding on matter, gas, dust, and sometimes entire stars that come too close and are mercilessly devoured. However, when we examine the case of TON 618, we encounter a mystery that challenges the limits of our understanding of the universe's evolution. If we consider the estimated age of TON 618 and the amount of matter it has accumulated, the mere passage of time seems insufficient to explain its colossal size. Were there exceptional conditions in the early universe that allowed this black hole to grow at a much faster rate than others? Some scientists suggest that, in its early moments, TON 618 may have gone through a phase of accelerated growth, devouring matter at unimaginably high rates. It has been proposed that, instead of being born from a massive star like smaller black holes, it may have formed directly from the collapse of a gigantic primordial gas cloud, skipping several intermediate stages. Is it possible that TON 618's feeding was so efficient that it surpassed the known theoretical limits, such as the Eddington limit, which establishes how much matter a black hole can consume before radiation pressure expels the remaining material? Some speculative models suggest that, in extremely dense and chaotic environments, this limit could be broken, allowing the black hole to grow by leaps and bounds. Imagine trying to fill a pool with a hose, and suddenly, someone opens a gigantic water gate. The filling rate multiplies, and in no time, the pool overflows. That could be how extreme the accretion rate of TON 618 was during its cosmic youth. However, the truth is that to this day, we still do not have a definitive answer. Each new observation of similar quasars challenges our ideas about the formation and growth of supermassive black holes. Was TON 618 an extraordinary case, or are there more such objects waiting to be discovered in the far reaches of the universe? Solving this enigma would not only help us understand the history of this quasar, but also decipher how the first galaxies evolved and, ultimately, the cosmos itself. The mystery of its growth remains one of the most fascinating and challenging puzzles in modern astrophysics. How hungry can a supermassive black hole get? TON 618 challenges our imagination with a veracity that surpasses almost any known limit in the universe. To understand the magnitude of its appetite, it is essential to talk about the accretion rate, the amount of matter this colossus absorbs each year. Is it possible for a single region of the cosmos to consume more material than hundreds of solar systems combined in an instant? In the case of TON 618, the answer is yes. The accretion rate of TON 618 is so extreme that, in astronomical terms, it amounts to devouring the equivalent of several suns in just 1 year. If we imagine a cosmic conveyor belt carrying gas, dust, and entire stars to the edge of a gravitational abyss, we could visualize, albeit approximately, the speed at which the central black hole of this quasar feeds. How is it possible that so much matter is available and does not disperse before being swallowed? The explanation lies in the chaotic and densely populated environment of matter surrounding these objects in the primitive universe, where collisions and mergers of galaxies created true banquets of material. But what really happens when this matter falls into the black hole? Before being irretrievably swallowed, the matter forms an accretion disk, a hot and luminous structure where particles spin at dizzying speeds and heat up to millions of degrees. This frantic dance of matter not only results in the emission of colossal amounts of energy, but also imposes a limit, the so-called Eddington rate. However, TON 618 seems to challenge even this theoretical limit. Observations suggest that its accretion rate approaches, or even temporarily exceeds, the maximum rate allowed by conventional physics, raising fascinating questions about the extreme conditions prevailing in its environment. Can a black hole grow this fast without self-destructing? In theory, if the accretion is too intense, the radiation released could expel the surrounding matter and slow the black hole's growth. Nevertheless, data indicate that TON 618 has managed to maintain an astonishingly high accretion rate for millions of years. This delicate balance between relentless gravity and the push of radiation is what has allowed the formation of one of the most massive and luminous objects ever discovered. The mystery of how TON 618 achieves this record continues to be the subject of intense research and reminds us how little we still know about the extremes of the universe. What happens when a source as powerful as a quasar radiates its energy into the environment? TON 618 stands out not only for its colossal size, but also for the intensity with which it bombards its host galaxy with radiation. The energy emitted by this quasar is so immense that, at its peak, it can outshine the combined brightness of all the stars in its galaxy. But how does such a display of radiation affect the surrounding space? The radiation from TON 618 spreads across the entire electromagnetic spectrum, from gamma rays to radio waves. High-energy photons, such as X-rays and ultraviolet rays, ionize the surrounding gas, stripping electrons from atoms and heating the interstellar medium to extreme temperatures. This has direct consequences. The gas that could form new stars is either dispersed or heated to the point that it cannot collapse under its own gravity. Thus, the quasar acts as a kind of cosmic oven that regulates star formation around it, preventing new generations of stars from being born. It's as if a colossal lighthouse, instead of guiding ships, evaporates the very sea that surrounds it. Can the radiation from TON 618 alter the evolution of its entire galaxy? The answer is yes. The winds and jets driven by the quasar can sweep enormous amounts of matter out of the galactic core, altering the chemical composition and internal dynamics over millions of years. This phenomenon, known as feedback, can even slow the growth of the central black hole, limiting the amount of material it can continue to devour. In a way, the quasar is both a destroyer and a creator. It halts star formation in certain regions, but it can also trigger shock waves that, elsewhere, compress gas and give rise to new stars. How far does the impact of the radiation from TON 618 reach? Studies suggest that its influence is not limited to its host galaxy, but can extend hundreds of thousands of light-years, altering the intergalactic environment. The light traveling from it can ionize distant gas clouds, transforming the structure of the cosmos on unimaginable scales. Thus, TON 618 is not only an astonishing object in itself, but it is also a true cosmic sculptor, capable of modifying the fate of vast regions of the universe with its relentless and devastating radiation. When we think of quasars, it's inevitable to wonder, what makes TON 618 so special compared to other giants of the cosmos? There are famous quasars like 3C273, the first to be identified and one of the most studied, or OJ287, known for its periodic outbursts. However, none match TON 618 in terms of the colossal mass of its central black hole and the almost unimaginable intensity of its luminosity. While 3C273 stands out for being visible even with small telescopes and is relatively close in cosmic terms, TON 618 resides at the edge of the observable universe and shines with a power that eclipses most of its peers. Is TON 618 simply a brighter quasar, or are there fundamental differences with other famous quasars? The answer is fascinating. The size of its black hole is so colossal that comparing it to that of 3C273 is like comparing a mountain to a hill. The black hole of TON 618 has an estimated mass of tens of billions of times that of the Sun, while that of 3C273 barely exceeds hundreds of millions. This chasm in mass scale makes TON 618 a true cosmic monster, capable of devouring amounts of matter equivalent to several solar systems in just a year. But what about its brightness? Some quasars, like PKS 21338, also emit jets of energy that travel at speeds close to light and generate radiation displays across different ranges of the electromagnetic spectrum. However, the glow of TON 618 is so intense that, despite being billions of light-years away, it outshines entire galaxies. If we could somehow bring this quasar closer to the Milky Way, its light would be so blinding that it would overshadow all the stars in the night sky combined. This energy comes from the matter spiraling into its black hole, releasing amounts of energy that challenge our everyday understanding. Another interesting comparison is with quasars like ULAS J1120 Plout288, discovered in the early universe. Although these quasars also host supermassive black holes and have intrigued astronomers due to their rapid growth, TON 618 remains an extreme case. The question persists: why are there so few quasars with such extreme masses? Scientists still debate whether TON 618 represents a statistical rarity or if there are other even more massive quasars waiting to be discovered in the far reaches of the universe. For now, TON 618 maintains its status as one of the most astonishing and challenging colossi for modern astrophysics. What would happen if a spaceship could approach TON 618? The question is intriguing because this quasar is one of the most extreme and hostile regions that the universe can offer. As one approaches its core, the environment becomes progressively more inhospitable. Even at distances of millions of kilometers from the center, the emitted radiation exceeds any imaginable protection. Ultraviolet light, X-rays, and gamma radiation would bathe any object, disintegrating materials and altering molecules in a matter of seconds. It is said that the luminosity of TON 618 is equivalent to that of hundreds of billions of suns condensed into a single point in space, meaning that long before being able to physically approach, the ship and its occupants would be vaporized by the intense energy bombardment. And what about gravity? The supermassive black hole at the heart of TON 618 has such a colossal mass that its gravitational pull distorts space and time around it. As one gets closer, the tidal forces intensify to inconceivable levels. These forces could stretch and compress any object, even before reaching the event horizon, in a process known as spaghettification. To put it into perspective, if the black hole at the center of TON 618 were placed in the solar system, its event horizon would span several times the orbit of Pluto. Getting closer would be like trying to resist the pull of an abyss that devours everything in its path, including light. But the danger does not only come from gravity or radiation. The accretion disk surrounding the black hole is a true cosmic hell. This disk, composed of gas and dust swirling at speeds close to that of light, reaches temperatures of millions of degrees. The friction between the particles generates bursts of energy that exceed the power of all the stars in an average galaxy. If a ship attempted to cross this disk, it would be instantly pulverized by the pressure, heat, and intense magnetic storms. Additionally, the relativistic jets, streams of matter expelled at nearly light speeds, could pierce through any object as if it were paper. Is there any safe place near TON 618? The reality is that at human scales, no known material could withstand the combination of radiation, gravity, and heat. Even communication or data transmission would be hindered by the extreme effects of the environment. In summary, approaching TON 618 would be facing one of the most lethal scenarios in the cosmos, where the laws of physics reach their limits and any attempt at direct exploration, at least with current technology, would be doomed to failure. The only way to study it is from a distance and through the light that miraculously manages to escape its environment to reach us. How big can a black hole be? When talking about cosmic scales, the human mind falls short. But the black hole TON 618 not only challenges the imagination, it shatters it. Its event horizon, the boundary beyond which nothing can escape, has an estimated diameter of over 130 billion kilometers. To put it in perspective, that's almost 20 times the diameter of our entire solar system, including the orbit of Pluto. If the Sun were at the center of this colossus, all the planets, comets, and even the Oort cloud would be comfortably trapped within its shadow. Now, how does this compare to other known giants? The black hole at the center of our galaxy, Sagittarius A, would seem like a speck of dust next to the magnitude of TON 618. Even the supermassive black hole in M87, famous for the first image of a black hole, is significantly smaller. If the event horizon of Sagittarius A were the size of a coin, that of TON 618 would be like a football stadium. The difference is so vast that it's hard to imagine both being, in essence, the same type of object. The accretion disk surrounding TON 618 is no slouch in terms of dimensions either. This disk of gas and dust, spinning at extreme speeds and reaching temperatures of millions of degrees, can extend for light years. If you tried to cross from one end to the other at the speed of light, it would take you over a year. And compared to the solar system, the accretion disk would wrap around it several times, as if our cosmic neighborhood were just a tiny dot lost within a gigantic spiral of energy and matter. In light of these figures, an inevitable question arises. Can the human mind truly comprehend such sizes? The scales of TON 618 force us to rethink what we believe we know about the universe. They remind us that, on the grand cosmic stage, even what we consider large is tiny compared to the true magnitude of the colossi that inhabit the depths of the cosmos. Thus, TON 618 becomes a true monument to universal excess, an entity whose dimensions defy any attempt at earthly comparison. How powerful can the gravity of an object in the universe be? TON 618 challenges us to imagine forces that go far beyond anything experienced on Earth. Its gravitational influence is so intense that not even light can escape if it crosses a certain limit around it. But how far does this influence really extend in space? To understand this, let's consider the size of the central black hole of TON 618. Its event horizon, that is, the boundary from where nothing can return, has an estimated radius of over 130 billion kilometers. This is several times greater than the average distance between the Sun and Pluto. If the solar system were near this colossus, it would all comfortably fit within the event horizon, with no possibility of ever escaping. But the gravitational influence of the black hole doesn't stop there. It extends far beyond that invisible boundary, affecting the movement of stars, gas, and dust throughout its host galaxy. Many wonder if it is possible to measure exactly how far the gravitational domain of TON 618 reaches. The answer depends on the amount of mass it can attract and dominate. In astronomical terms, we talk about the sphere of influence of the black hole, a concept that indicates the region where its gravity surpasses that of the rest of the galaxy. In the case of TON 618, that sphere could have a diameter of light years, encompassing enormous regions and determining the fate of matter on galactic scales. Everything that orbits within that zone is doomed to feel the irresistible pull of this giant. Now, how does this affect the environment? The extreme gravity of TON 618 not only traps a vast amount of matter, but can also distort the space-time around it. Tidal effects, for example, are so intense that any object that gets too close would be stretched and torn apart long before reaching the event horizon. Furthermore, its gravitational field can bend the path of light coming from more distant objects, creating phenomena like gravitational lenses, where light curves and multiplies the images of galaxies located behind the quasar. The gravitational influence of TON 618 is, ultimately, one of the most formidable in the known universe. Its reach not only defines the behavior of its galaxy, but also forces us to rethink the limits of what is possible in terms of cosmic force and power. Could there be something even more dominant in some remote corner of the cosmos? The search continues, but for now, TON 618 stands as a true gravitational emperor. For years, quasars have fascinated astronomers not only for their incredible brightness, but also for the questions they raise about the composition and fate of the universe. One of the most intriguing questions is, what connection could these colossal objects have with dark matter and dark energy? To understand the magnitude of this issue, let's first remember that visible matter, like stars, planets, and ourselves, represents a tiny fraction of the cosmic total. Most of the universe is made up of dark matter and dark energy, two mysterious components that we cannot observe directly, but whose presence we deduce from their gravitational effects and the acceleration of the cosmos expansion. Can a quasar like TON 618 help us decipher the secrets of dark matter? Scientists have proposed that quasars, due to their extreme brightness and the vast distances at which they are found, act as cosmic beacons that illuminate the space between galaxies. By analyzing how the light from a quasar passes through clouds of gas and regions where dark matter is suspected to exist, astronomers can detect small variations and absorb vital information. It's like shining a flashlight through a fog. The light that reaches us gives us clues about what is in that invisible path. Thus, by carefully studying the spectra of such distant quasars, it is possible to map the distribution of dark matter in the early universe. But what about dark energy? This mysterious force, responsible for the acceleration of the universe's expansion, presents an even greater challenge. Quasars, like TON 618, allow us to observe the universe as it was billions of years ago. By comparing the distance and redshift of many quasars, scientists can reconstruct how the speed of space expansion has changed over time. If dark matter acts like a kind of cosmic glue, dark energy would be like a spring pushing everything outward. Analyzing the distribution and brightness of quasars in different cosmic epochs helps refine models of how these two invisible components interact and how they have shaped the evolution of the cosmos. Could TON 618 be key to discovering the true nature of dark matter and dark energy? Although we do not yet have a definitive answer, its study is essential for testing the most advanced theories of physics. The most massive and distant quasars become natural laboratories, allowing astronomers to observe extreme phenomena that would be impossible to recreate on Earth. Every piece of data obtained about their environment, their growth, and how they affect the matter around them adds valuable information to a puzzle that remains incomplete. Ultimately, The relationship between quasars like TON 618, dark matter, and dark energy is one of the great enigmas of modern astrophysics. Through their light, these cosmic titans offer us windows into the deep past of the universe and bring us, if only a little, closer to understanding what everything that exists is truly made of. Research continues, and with each new advance, TON 618 solidifies its role as a key piece in the quest for answers about the structure and fate of the universe. What makes such a distant and colossal object as TON 618 capture the imagination not only of astronomers, but also of popular culture? Although its name may sound technical and reserved for the scientific realm, TON 618 has become a sort of legend among space enthusiasts, appearing in forums, documentaries, science fiction novels, and even video games. Why is it so fascinating? The answer lies in its extreme nature. A quasar that challenges the limits of what we understand about size, energy, and the age of the universe. It is the archetype of the cosmic giant, a true interstellar monster that seems to have come from the imagination of a Hollywood screenwriter. In some novels and science fiction stories, TON 618 has been portrayed as the setting for galactic battles or as the center of advanced civilizations exploring the secrets of space-time. Could there be life near such a gravitational abyss? Although science dismisses it, fiction has played with the idea that super-advanced civilizations could harness the energy of a quasar as an almost limitless power source. In video games and animated series, TON 618 is sometimes used as a reference to illustrate the unknown, as a symbol of the vast and mysterious that still remains to be discovered in the cosmos. Music and visual art have also found inspiration in this quasar. Some concept albums in electronic music and progressive metal have adopted the name TON 618 or dedicated pieces to its enigmatic presence. For many artists, it represents the ultimate frontier, a reminder that our universe is much larger and stranger than any human could ever imagine. The mere act of pronouncing the name TON 618 evokes a sense of vertigo and wonder, like gazing at the night sky for the first time from a completely dark place. On social media and scientific outreach platforms, TON 618 often appears on lists of the most extreme objects in the universe, alongside other phenomena like neutron stars or pulsars. Can a black hole be so large that it could swallow entire solar systems? TON 618 is the favorite answer of many science communicators to illustrate the true meaning of the colossal. Thus, this quasar has transcended the academic realm and become a modern icon of the mysteries of the cosmos, fueling both scientific curiosity and human creativity. In short, TON 618 has earned a special place in popular culture, not only as an astronomical record, but as a symbol of the unexplored and the immeasurable. It reminds us that, although science advances every day, there are still abysses in the universe that we have yet to comprehend, and that these enigmas can become a source of inspiration for the collective imagination. Studying an object as distant and colossal as TON 618 presents challenges that often exceed even the imagination of astronomers. How is it possible to analyze in detail a quasar that is billions of light years away, in a region of the universe where the light we receive left when the cosmos was just a fraction of its current age? The first obstacle lies in the extreme distance. The farther away an object is, the weaker and more distorted its signal becomes. It's like trying to decipher a conversation in a packed stadium from the other end, where the echo and noise make it almost impossible to distinguish the original words. Moreover, the light from TON 618 has traveled for eons through the expanding universe. During that journey, not only has it weakened, but it has also undergone a phenomenon known as redshift, which stretches the wavelengths and shifts the information to regions of the spectrum that require very sensitive instruments to be detected. Telescopes must be capable of capturing signals in ranges that go from ultraviolet to far infrared. But even the best ground-based observatories face interference from the Earth's atmosphere, which absorbs and distorts part of the cosmic light. That's why space telescopes are used, whose access is limited and whose observational capacity must be shared among multiple scientific projects? And how do we determine the mass of such a monstrous black hole? Here comes another challenge. We cannot observe the black hole directly. Scientists must interpret the light emitted by the accretion disk surrounding it, analyzing patterns in the spectrum and the dynamics of gas clouds. But these methods depend on theoretical models that, although accurate, still have considerable margins of error. The extreme conditions near a quasar challenge our understanding of physics, and any small uncertainty in the data can lead to very different estimates of its size or luminosity. Finally, the very environment of TON 618 adds complexity. Is it possible to separate the light from the quasar from that of its host galaxy and other nearby sources? The answer is not straightforward. Observations can easily be contaminated by the presence of interstellar dust and by the overlap of other objects in the line of sight. Additionally, the variability of quasars, which can change brightness on relatively short timescales, poses an additional challenge for obtaining accurate and consistent measurements. All of this makes the study of TON 618 a true cosmic puzzle, where each advance depends as much on the available technology as on the creativity and ingenuity of the researchers. What tools will we need to unravel the deepest secrets of TON 618? Despite current advancements, the telescopes we have today barely manage to capture a fraction of the details of this cosmic colossus. However, the next generation of instruments promises to revolutionize our observational capabilities. Space telescopes like the James Webb are already opening unprecedented windows to the distant universe. But scientists around the world are already planning even more powerful devices capable of seeing beyond what we ever imagined. Will it be possible to directly observe the environment of the central black hole of TON 618? One of the most ambitious bets is the extremely large telescope, known as ELT, for its acronym in English. With a mirror nearly 40 meters in diameter, this ground-based instrument will allow us to capture light so distant and faint that, in comparison, current telescopes would be like trying to see a firefly in a lit city. Thanks to its advanced adaptive optics systems, the ELT will be able to correct distortions caused by the Earth's atmosphere, obtaining much sharper and more detailed images of distant quasars. Can this telescope help us accurately measure the mass and spin of the black hole at the heart of TON 618? But exploration will not be limited to visible light. Instruments like the Athena X-ray Observatory, planned by the European Space Agency, will allow us to analyze the X-rays emitted by the accretion disks around supermassive black holes. These X-rays contain invaluable information about the extreme temperatures and violent processes occurring near the event horizon. If we manage to decipher these signals, we could better understand how TON 618 has grown so much and so quickly, and how it interacts with its galactic environment. What hidden mysteries will high-energy radiation reveal to us? Radio telescopes will also play a fundamental role. Projects like the Event Horizon Telescope, which has already managed to photograph the shadow of a black hole in another galaxy, could in the future combine with other antennas to form even more powerful networks. Thus, through the technique of very long baseline interferometry, we could obtain images with an unprecedented resolution, getting closer to the finest details of the quasar. Imagine being able to see, with the precision of distinguishing a coin on the moon from Earth, the internal structure of the relativistic jets of TON 618. How far will the boundaries of our observation reach? Finally, artificial intelligence and machine learning will be indispensable allies in analyzing the avalanche of data generated by these future instruments. Algorithms will be able to identify patterns, anomalies, and fleeting events that the human eye would overlook. All of this will bring us, step by step, closer to a deeper understanding of colossal quasars and therefore of the very history of the universe. Who knows what new surprises await us when we point our technological eyes toward the far reaches of the cosmos? How is it possible to study a cosmic monster located billions of light years away, whose true nature is beyond any direct experiment? This is where simulations and theoretical models come into play. fundamental tools of modern astrophysics. Scientists use supercomputers capable of performing millions of calculations per second to recreate, in a virtual environment, the extreme conditions surrounding quasars like TON 618. But how can they be sure that these simulations reflect reality? The key lies in combining precise astronomical observations with the laws of physics we know, such as Einstein's general relativity and plasma physics. One of the big questions is how a black hole can grow to such a colossal mass in such a short cosmic time. For this, theoretical models explore different scenarios: continuous accretion of matter, mergers of smaller black holes, or perhaps still unknown mechanisms. The models allow testing these hypotheses safely, without the need to approach these lethal objects. For example, researchers can vary the amount of gas available in the simulation, or modify the speed at which the black hole consumes matter, observing how the brightness and emissions of the quasar change. Did you know that simulations also predict the formation of powerful relativistic jets that emerge from the poles of the black hole? These jets, capable of traversing entire galaxies, are recreated in computational models that consider extreme magnetic and relativistic effects. Thanks to these virtual experiments, it is possible to understand why some quasars exhibit more intense jets than others and how they interact with the interstellar medium, even influencing the formation of new stars. But simulations are not only useful for explaining what we already see, they are also a window into the unknown. Could there be even more massive quasars, or ones with unexpected properties? Theoretical models explore the limits of physics under extreme conditions, helping scientists predict phenomena that have not yet been observed. Thus, each advance in simulation capability and the development of more precise models brings us a little closer to deciphering the mysteries of giants like TON 618, allowing theory and observation to work together in the exploration of the deeper universe. Is it possible that there are even larger quasars than TON 618? This is one of the questions that intrigues modern astronomers the most. Considering that the observable universe contains hundreds of billions of galaxies, each with the potential to host active nuclei, the possibility of discovering even more colossal quasars cannot be ruled out. But what factors limit the size of a quasar and, in particular, that of its central black hole? The growth of a supermassive black hole depends on the amount of material available in its surroundings and how quickly it can consume it. However, there is a limit imposed by the so-called Eddington luminosity. If the black hole absorbs matter too quickly, the resulting radiation can expel the surrounding gas, hindering its own growth. It's like trying to fill a bathtub while the drain is open. There comes a point where the water won't rise any higher, no matter how much you increase the faucet. Thus, while physics suggests that even larger black holes may exist, nature itself puts a brake on their unchecked expansion. Despite these limitations, astronomers believe that there could be more massive quasars in corners of the universe yet to be explored. The primitive universe was an extremely dynamic place, where collisions and mergers of galaxies were much more frequent. In these chaotic environments, the formation of supermassive black holes, even larger than that of TON 618, may have been possible. However, the light from these objects would be so distant and redshifted that our current telescopes could barely detect it. Could they be hiding, waiting to be revealed by the next generation of observatories? The search for even larger quasars poses fascinating technical and theoretical challenges. If we ever detect one that is more colossal, it will be a unique opportunity to test our theories about the formation of extreme structures in the cosmos. Furthermore, the discovery of a more massive quasar would force us to rethink the current limits of physics and astrophysics, challenging our ideas about how black holes grow and how galaxies evolve. Are we perhaps at the tip of the iceberg? Or does TON 618 represent a record that is difficult to surpass in the vastness of the universe? The answer, for now, remains hidden among the depths of the cosmos. What is the true impact of a colossal quasar like TON 618 on the evolution of the universe? To understand it, we must first consider that these objects are not mere cosmic beacons. TON 618, with its incredible power, acts as a gigantic factory of energy and matter in the early cosmos. Its enormous central black hole devours matter at astonishing speeds, releasing amounts of energy that defy imagination. But why is this relevant to the evolution of the entire universe? Quasars, like TON 618, play a fundamental role in regulating galaxy growth. The process is a kind of cosmic feedback. The radiation and winds generated by the accretion disk and relativistic jets can heat and expel interstellar gas, inhibiting the formation of new stars around it. It's as if TON 618 were a cosmic gardener, pruning excess galactic growth and shaping the architecture of galaxies in its neighborhood. This mechanism helps explain why not all galaxies become chaotic giants and why galactic evolution follows certain observable patterns. But can a single quasar influence the very fabric of the universe? The answer is more fascinating than it seems. TON 618, like other extremely luminous quasars, contributes to the rionization of the universe, a key process in cosmic history. During the early stages of the universe, the intense radiation from these objects helped transform neutral gas into ionized gas, allowing light to travel freely through space. Without quasars like this, the universe would have remained much darker and more opaque for billions of years. Moreover, TON 618 is a window into the deep past. Its light, which travels billions of years before reaching us, allows us to observe what the first galaxies and black holes were like. It is, in essence, a time capsule that reveals how the most extreme objects have shaped the large-scale structure of the cosmos. How far does its influence reach? Its expelled energy and matter can travel immense distances, enriching the intergalactic medium with heavy elements and setting the stage for the formation of future stars and planets. In summary, TON 618 is much more than an isolated and bright object. It is a key player in the evolution of the universe, capable of altering the fate of entire galaxies, contributing to the deepest changes in the composition and transparency of the cosmos, and providing us with essential clues about our own cosmic history. Its existence reminds us that, in the universe, solitary giants can have consequences that resonate throughout all eternity. What fate awaits a colossus like TON 618? The life of a quasar is, in cosmic terms, surprisingly brief. Although it may seem eternal from our limited human perspective, these objects go through different stages until they ultimately fade away. A fundamental question is, how much longer can TON 618 continue shining with such intensity? The answer largely depends on the fuel that powers it, the gas and dust that inexorably fall toward its central black hole. When this reservoir of material runs out, the quasar will cease to emit the colossal amount of energy that characterizes it, and gradually its glow will fade. But what happens to the gigantic black hole that lies at the heart of TON 618? Once the quasar extinguishes its light, this gravitational monster will not disappear. On the contrary, it will remain silent and dark as a remnant of a turbulent past. Supermassive black holes, like the one in TON 618, can persist for billions of years, slowly growing if they manage to capture new matter, or simply remaining inactive. It is fascinating to think that, in the distant future, this black hole could merge with others if its host galaxy were to collide with another, a process known as galactic merger, common in the evolution of the cosmos. Could TON 618 awaken again and unleash its quasar fury once more? It's possible, but unlikely. If at some point a significant amount of gas were to be thrown toward the black hole, it could briefly reactivate. However, most quasars only experience one active phase in their existence. It's like a bright spark in the darkness of the universe, fleeting compared to the vastness of cosmic time. The most likely fate is that, over the eons, TON 618 will become a silent, supermassive black hole, invisible to most instruments, but always present as an indelible mark of the early history of the universe. In the very, very long term, even the most massive black holes face their own end. Hawking radiation theory predicts that, on inconceivably long timescales, black holes may slowly evaporate, losing mass until they completely disappear. However, this process would take such an immense amount of time that by then, the stars will have died, and the universe will be a cold, dark place. Thus, TON 618, which today dazzles as one of the most luminous and extreme objects in the cosmos, will end its journey in a silent fate, reminding us of the ephemeral nature of even the most colossal phenomena in the universe. What makes TON 618 so special, beyond its colossal size? To begin with, its estimated mass is astonishing, approximately 66 billion times that of the Sun. To put this into perspective, if the Sun were the size of an orange, the black hole TON 618 would be larger than an entire mountain. This fact makes it not only one of the most massive quasars, but also one of the most extreme objects ever detected by humanity. Another fascinating curiosity is the age of the light we receive from TON 618. What we observe today left there when the universe was only about 5 billion years old. In other words, we are seeing a kind of cosmic photograph of a deeply remote past when the Milky Way didn't even resemble what it is today. If any civilization were currently near TON 618 and looked towards Earth, they would see our planet in a very early stage, perhaps before the emergence of the first complex animals. TON 618 has also been the subject of intense scientific debates. How is it possible for such a massive black hole to have formed so soon after the Big Bang? This enigma has led astronomers to reconsider some models about black hole growth and the early evolution of galaxies. Some suggest that there may have been exceptional conditions in the early universe that allowed for the birth of these giants, while others speculate about even more exotic and unknown processes. Finally, there is the curious fact that, despite its extreme brightness, TON 618 is completely invisible to the human eye. Its light is shifted towards ultraviolet and infrared due to the expansion of the universe. If we could get close to it, the radiation would be so intense that it would destroy everything around it. But from Earth, its presence is barely a whisper lost among millions of galaxies. Thus, TON 618 remains a reminder of how extraordinary and mysterious the universe can be. When we talk about the expansion of the universe, a fascinating question arises. How does a distant and colossal object like TON 618 help us understand this cosmic phenomenon? The answer lies in the light it emits and the distance at which it is located. TON 618 is one of the most distant quasars we have managed to detect, and its light has traveled billions of years before reaching us. This not only means that we see it as it was in the remote past, but it also allows us to measure how much the universe has expanded since then. What is special about the light from TON 618? By analyzing its spectrum, astronomers detect a strong redshift. It's like hearing an ambulance moving away and the sound becoming deeper. In the universe, the light from distant objects stretches to longer wavelengths due to the expansion of space itself. The greater this redshift, the faster the object is moving away and the older the moment when its light was emitted. TON 618 has one of the highest known redshifts, making it a key beacon for measuring the expansion rate of the cosmos in very early times. Can a single quasar teach us about the fate of the universe? Surprisingly, yes. Observing quasars as distant as TON 618 allows scientists to compare expansion rates at different moments in cosmic history. Thus, they can reconstruct how the expansion rate has changed and search for clues about dark energy, that mysterious force that seems to accelerate the growth of the universe. Each measurement, each distant quasar, is like a mark on the cosmic measuring tape that helps us understand the past and predict the future of the universe. Moreover, studying the light that reaches us from such remote places as TON 618 is similar to looking at an old photograph from our childhood. It not only reveals what the universe was like in its early days, but it also shows us how cosmic structures have evolved over unimaginable eras. TON 618 with its imposing brightness and astonishing distance, is a direct window into a young and expanding universe, providing irreplaceable data to decipher the mysteries of evolution and the ultimate fate of the cosmos. What exactly is the event horizon, and why is it so fascinating in the case of a colossus like TON 618? The event horizon is an invisible boundary that surrounds every black hole. It is the ultimate limit. Once anything, be it matter, light, or even information, crosses that line, there is no turning back. From the outside, it appears as a spherical surface, but in reality, it is a region of space where gravity is so intense that nothing can escape its pull. If we compare it to a waterfall, it would be the point where the water falls and can no longer go back, inexorably dragged into the abyss. Have you ever wondered what the size of the event horizon of TON 618 is? This limit is truly astonishing. Its Schwarzschild radius, which marks the distance from the center of the black hole to the event horizon, far exceeds the size of our entire solar system. To give you an idea, if the Sun were replaced by the black hole of TON 618, the event horizon would extend well beyond the orbit of Pluto. We are talking about a sphere of darkness so monumental that it could swallow several complete solar systems. But what really happens near the event horizon? The laws of physics, as we know them, begin to twist. Time slows down drastically for anyone approaching. As seen from the outside, an object would appear to freeze at the edge, never quite crossing over. Light bends and stretches until it becomes invisible. If we imagine a ship approaching, as it nears the horizon, the ship would become increasingly faint and red, fading away until it disappears before our eyes. It is a scenario where space and time merge in a strange dance, governed by Einstein's general relativity. Now, why is the event horizon so relevant for understanding objects like TON 618? Because there lies the fundamental mystery of black holes. Everything that happens within that limit remains hidden forever, beyond the reach of any direct observation. The event horizon marks the threshold between what we can know and what remains eternally unreachable. It is the ultimate frontier of the cosmos, the place where information seems to be lost and where the laws of physics are tested in ways we are just beginning to imagine. In the case of TON 618, this gigantic horizon reminds us of how small we are in the face of the most extreme structures of the universe. What happens when everyday physics begins to fail and only relativity can explain what occurs? In the vicinity of TON 618, extreme relativistic effects manifest in every corner of space-time. Gravity is so intense in this environment that the very fabric of the universe bends in ways that are almost incomprehensible to our intuition. Here, light and time behave very differently from what we experience on Earth. But how is this phenomenon truly perceived from the perspective of relativity? Approaching the supermassive black hole at the heart of TON 618 means facing time dilation. The closer you are to the event horizon, the more slowly time passes compared to a distant observer. In other words, if a clock were to travel toward the edge of the black hole, it would appear to tick more and more slowly from the viewpoint of someone far away. In extreme cases, time would come to a complete stop at the event horizon, at least in the eyes of an external observer. This temporal difference is so pronounced that, in theory, someone very close to the black hole could see the distant universe's future advancing at a dizzying pace. But relativity does not only affect time. What happens to light in these domains? The gravity of TON 618 is capable of bending light rays, causing images of nearby objects to distort and multiply. This phenomenon, known as gravitational lensing, causes light attempting to escape the black hole's environment to be stretched to the extreme, shifting its colors toward the red in what is called gravitational redshift. Thus, the information we receive from Earth has already been profoundly altered by this cosmic dance of light and gravity. The accretion disk surrounding the black hole is also a stage for astonishing relativistic effects. Gas and dust particles swirl at speeds approaching that of light, and as a result, they experience an increase in apparent mass and emit radiation in an extreme energy range. Furthermore, the light emitted by these particles is modified by the relativistic Doppler effect. The part of the disk that is moving toward us appears brighter and bluer, while the part that is moving away appears dimmer and redder. This contrast allows astronomers to measure the rotation and structure of the disk, thus deciphering the secrets of one of the most extreme environments in the universe. And what about space itself? The presence of a black hole as massive as that of TON 618 causes such distortion that space seems to compress and stretch in ways that are almost impossible to imagine. An object falling toward the black hole would experience such intense tidal forces that it would literally be stretched like spaghetti, in a process known as spaghettification. These forces, along with the effects of relativity, make TON 618 a natural laboratory where the limits of physics as we know it are tested. Could it be that within these extremes lie clues about new laws of the universe yet to be discovered? What connection can a colossal quasar like TON 618 have with the formation of the elements that make up the universe? It may seem surprising, but the answer lies in the violence and immense energy that these objects release. When we think of element creation, the first things that usually come to mind are stars or supernovae. However, quasars, with their powerful relativistic jets and incandescent accretion disks, also play a fundamental role in the chemistry of the cosmos. The processes occurring in the extreme environment of a quasar like TON 618 are capable of profoundly altering the matter that surrounds them. The intense heat and ionizing radiation from its accretion disk can strip electrons from atoms, fragment molecules, and trigger nuclear reactions in the surrounding gas. What does this mean? That the heavy elements forged in previous generations of stars can be scattered throughout the host galaxy and even into intergalactic space thanks to the powerful winds and jets that emerge from the active core. Can a quasar contribute to the creation of new elements? In a way, yes. Although most nucleosynthesis occurs in stars and supernova explosions, the energetic environment of a quasar can facilitate the mixing and transport of these materials. The powerful jets expel matter at speeds close to the speed of light, carrying elements like carbon, oxygen, or iron to remote regions of the universe. Thus, TON 618 not only illuminates the cosmos, but also seeds space with the necessary ingredients for the formation of new stars, planets, and even life. Over millions of years, this redistribution of chemical elements allows entire galaxies to evolve and enrich their composition. Thanks to the action of quasars like TON 618, the raw material of the universe is recycled and dispersed as if they were gigantic cosmic stirrers. Without these extreme processes, the chemical diversity we observe in the universe would be much more limited. Therefore, every atom of oxygen we breathe or carbon in our bodies could, in part, have been propelled through space by the fury of a distant quasar. In summary, quasars are not only beacons of light that allow us to peek into the deep past of the universe, they are also engines of chemical change and unwitting architects of matter. TON 618, with its impressive power, is part of that invisible network of cosmic processes that from the farthest corners help forge and distribute the elements that make existence itself possible. Who would have imagined that at the heart of such a cosmic monster lies one of the keys to understanding where the matter that composes us comes from? Is it possible that, in some distant corner of the universe, life exists near a quasar as extreme as TON 618? To answer this question, we must first ask ourselves, what does life as we know it need? Earthly life depends on relatively mild conditions, moderate temperatures, a stable source of energy, complex chemical elements, and, above all, protection from extreme radiation. But TON 618 is anything but a peaceful environment. This quasar is one of the most energetic and violent objects in the cosmos. Its supermassive black hole devours matter at a dizzying rate, releasing unimaginable amounts of radiation in the form of X-rays, ultraviolet light, and other forms of lethal energy. If Earth were to orbit near an object like TON 618, the atmosphere would be quickly destroyed by radiation, and any form of life would be annihilated in seconds. can there then be hope for life near such a hostile environment? Scientists have explored the possibility of protected niches, such as planets with incredibly dense atmospheres, or worlds submerged beneath thick layers of ice or rock. However, even in those cases, the intensity of radiation and gravitational instability would make the emergence and persistence of life practically impossible. Another intriguing question is that of the chemical ingredients. Quasars, by accelerating and heating the gas around them, contribute to the dispersal of heavy elements in the universe. However, the immediate region around TON 618 is so chaotic that complex molecules would be quickly destroyed before having a chance to organize into living structures. It's like trying to build a sandcastle in the middle of a storm. Any attempt to form something lasting is thwarted by the violence of the environment. Finally, some researchers wonder if there could be radically different forms of life than ours, capable of withstanding or even harnessing the extreme energy of a quasar. Could there be organisms that survive in plasma, feeding off radiation? For now, this belongs more to the realm of science fiction than science. As far as we know, no known mechanism would allow for the existence of life under these conditions. Thus, although the universe constantly surprises us, everything points to TON 618 being one of the least hospitable places for life, at least as we imagine it. However, the question remains open, reminding us how little we know about the infinite possibilities of the cosmos. What makes TON 618 a true gem for science? It's not just its colossal size that fascinates astronomers, but the range of cosmic mysteries it has helped unveil. This quasar, with its supermassive black hole at its center, has become a kind of natural laboratory for studying the extreme limits of the universe. By analyzing it, scientists have been able to test theories about the formation and growth of black holes in the early cosmic times. Could there be even larger and older objects? TON 618 pushes us to question what the true limits of nature are and how far galactic evolution can go. One of the greatest scientific legacies of TON 618 is its role in understanding the ultra-fast growth of supermassive black holes. The fact that it has accumulated so much mass in a relatively short period after the Big Bang raises fundamental questions. How could it devour such a large amount of material in such a short time? This enigma has driven the development of new models and simulations that explore not only the accretion of matter, but also the processes of galaxy mergers and the extreme conditions of the early universe. TON 618 serves as a kind of benchmark to calibrate and challenge our theories about cosmic evolution. How has our view of the cosmos changed thanks to TON 618? By observing its light, which has traveled for billions of years, astronomers have refined techniques for measuring immense distances and have perfected the study of redshift. Furthermore, this quasar has allowed researchers to investigate how the radiation from an active galactic nucleus can influence or even hinder star formation in its host galaxy. Thus, TON 618 has helped reveal the complex relationship between black holes and galaxy evolution, an interaction that is key to understanding the large-scale structure of the universe. Finally, the legacy of TON 618 is not limited to theoretical astrophysics. It has also inspired the development of more advanced instruments and motivated international collaboration among observatories and scientists around the world. Each observation of this colossal quasar presents a technological challenge that drives innovation. And like a window into the most distant past, TON 618 will continue to guide generations of researchers in the quest for answers to the deepest mysteries of the universe. Its legacy is, in essence, that of a beacon illuminating the limits of our knowledge and inviting us to keep exploring the unknown. What makes an object in the universe capture the attention of astronomers, scientists, and dreamers alike? TON 618 is the answer to that question. This colossus, hidden in the vastness of the cosmos, challenges our understanding of the limits of energy, matter, and time. Its supermassive black hole, whose mass defies any everyday comparison, represents one of the deepest enigmas of modern astrophysics. How is it possible that a structure of such magnitude formed so early in the history of the universe? What secrets does it hold about the birth of galaxies and cosmic evolution? At the heart of TON 618 beats a force capable of devouring entire stars and shaping its surroundings on scales that escape our imagination. To put it in perspective, if its black hole were to replace the Sun in our solar system, it would not only consume all the planets, but its event horizon would even engulf the orbit of Pluto. This unfathomable abyss acts as a natural laboratory, allowing scientists to study physical phenomena that are impossible to recreate on Earth. What really happens beyond the event horizon? Can the physics we know describe the extreme processes that occur there? The light from TON 618 travels for billions of years before reaching us, bringing with it invaluable information about a time when the universe was young and turbulent. Its study not only reveals the mechanisms that can fuel the brightest quasars, but also helps us understand the expansion of the universe itself. Isn't it astonishing that by observing this distant bright point, we are looking back in time, witnessing the echo of events that occurred when our solar system didn't even exist? Despite the challenges of studying such a distant and extreme object, TON 618 has left an indelible mark on the history of astronomy. It has driven the creation of new technologies, stimulated revolutionary theories, and above all, reminds us that the universe is full of mysteries waiting to be discovered. Could we one day find an even more colossal quasar? What new questions will arise when we manage to unravel the true origin of giants like this? TON 618 is undoubtedly a permanent invitation to curiosity and wonder, a reminder that, although we think we have seen it all, the cosmos always has something unexpected to offer.